Hey, welcome back, astronomy friends. This is the second of our lessons for the week, and this is going to be all about angular measurement and magnitudes. This is kind of a strange thing, probably something you haven't quite thought about before, but it's a little bit mathy, so this might be a little bit tricky, but I do think you're going to understand it, and we do need to understand what angular measurement and magnitude is all about. So let's take a look at what is going on here. Okay, so I want you to imagine looking at the moon in the sky, and oh wow, that's a really low resolution picture. Sorry about that. But when you look at the moon in the sky, it kind of seems big, a full moon, but it actually is not that gigantic. You've probably noticed this if you've ever taken a photo of it with your phone. It's actually kind of small in the frame. Even if you blow it up, it's fairly small in the frame. It's why you need a telescope to see any detail. The moon has an angular size of about half a degree, which is also about the same angular size as the sun. What that means is, if you can tell from the picture, that if you were looking at the moon and you look at the left side of the full moon and the right side of the full moon, this angle in here, if you could imagine kind of measuring it with a protractor, is what we call the angular size of the moon. So yeah, and that's about half a degree. It's also, again, about the same for the sun. What does that mean? Well, angular size is a way of describing just how much of an angle an object seems to cover in front of you. Sometimes we use the word subtend, how much of an angle subtends in the sky. And it is, of course, related to the actual size of the object, but also how far it is away. So I've used these numbers before, that the moon and the sun have about the same angular size. The moon's diameter is about 1/4 that of, 1/400th that of the sun. But the sun is also about 400 times further away than the moon is, and those two effects allow us to have eclipses every year and a half or so, lunar and solar. Okay, so this angular size business is going to be important because we can use it to calculate distances. Well, let's talk about the math that goes back to the early Babylonians. You're familiar with some of this. There's 360 degrees in a circle. Why is that? Well, there's a whole lot to be said about it, but the Babylonians were a base 60 group of folks. So you can do numbers in all sorts of bases. Base 2 if you like binary, base 8 if you like octal, base 16 if you like hexadecimal. You're probably most used to base 10. But base 60 was another way to do it. Not so common anymore. Anyway, if you use base 60, you end up with getting 360 degrees in a circle. And of course, I'm glossing over the details here. Now, each degree can be further divided into what we call 60 minutes. Actually, they're called arc minutes. 60 arc minutes in a degree, and each arc minute can be subdivided into 60 arc seconds. That means there's 60 times 60, or 3600 arc seconds in 1 degree. And we use these designations when we're trying to figure out things like how big something in the sky is, or more often we use it to determine how far something is away based on how much it moves. More about this shortly. So here's just a couple of rough approximations to think about. You don't have to write any of this down, but if you extend your fist at arm's length, that gives you an angle of about 10 degrees. If you extend your thumb at arm's length, that's about 2 degrees. That's why you can easily block out the moon or the sun with your thumb, although you want to close one eye for the total effect. And again, the moon and sun both subtend an angle of about half a degree. Now, human eye resolution, which we would say is the ability to distinguish between two adjacent objects, that's limited to about 1 arc minute. And in theory, that's roughly the diameter of a dime at 60 meters. If you can imagine standing in my classroom, right outside my classroom door, and trying to see somebody down the hall, probably close to the theater, then that's about the best you're going to be able to see. If they're holding a dime, you might be able to tell. If you have really good eyes, you might be able to tell that that's something that they're holding. But honestly, given the size of the retina, you're limited to something a little bit lower than that. So when we want to have better resolution, we got to have bigger eyes. We can't make our eyes bigger, but we can make telescopes that have way more light gathering ability. We have other limitations, of course. The Earth's atmosphere limits the details that we can get. So this is kind of like having a diameter of a dime 7 kilometers away, or human hair 2 football fields away. That's usually reduced a bit because of atmospheric turbulence. Well, brand new unit. I mentioned this unit earlier, the parsec. Here's where it comes up. Here's how we're going to define it. Now, if you have a distance that a star happens to be, and it subtends an angle of 1 arc second, if it is if you have moved 1 AU, we define that as 1 parsec. Now that was pretty quick, so let me talk about some details here. Here's the sun. This, I know I made this orbit looking circular. Sorry about that. It's elliptical, but for the sake of argument, we're going to make it kind of circular here. And this distance is 1 astronomical unit. And let us assume that the Earth moves from there over to there, which has a distance of 1 AU. And if the distance is such that this angle in here is going to be 1 arcsecond, then this is defined as being 1 parsec, which actually stands for having a parallax angle of 1 arcsecond. Now that works out to be, if you do the math, about 3.25 or 3.26 light years. But the beautiful thing about this is that there's a nice simple relationship that I'm going to show you. Here it is. The distance to anything in parsecs is 1 over the parallax angle in arcseconds, which is really kind of nice and convenient. Like, for example, let's say a star has a parallax angle of 0.5 arcseconds, then it is 1 over 0.5 parsecs away. 1 over 0.5 is 2 parsecs. So it's a really easy way to determine the distance to something based on the parallax angle in arcseconds. And again, 1 parsec is about equal to 3.26 light years. This technique generally only works for the nearest things, but still it's a pretty cool technique, and it's a nice simple way to do it mathematically. Well, as long as you have a calculator handy. And as I say, the beauty of the parsec unit is that we can find the distance to stars just based on their parallax angle. And that's the angle shift over a few months. And the picture I just showed you, it's basically 3 months, although you can do it differently. All right, part 2. Let us talk about magnitude. I have discussed magnitude before when we were looking at star charts. Star charts, we indicate the magnitude by using bigger or smaller dots. The bigger dots have greater apparent magnitude. The smaller dots have smaller apparent magnitude. And basically all that is a way of expressing how bright the star appears to be. There's 2 types of magnitude, however. You've got apparent magnitude, which is how bright it appears to be from Earth. And then there's absolute magnitude, which expresses how bright it actually is. The apparent magnitude is clearly related to the absolute magnitude and how far away it is. They are intimately related, in fact. So I'm going to just jump back here, 2,500 years or so, to friendly neighborhood Hipparchus. Hipparchus came up with the idea of magnitude. He classified things as bright or small, but a few hundred years later, Claudius Ptolemy, in his Almagest, which was the great pre-telescope scientific work all about astronomy, he classified things with numbers 1 to 6. 1 was the brightest and 6 was the dimmest, and he estimated that the brightest objects were 100 times brighter than the faintest. And that standard is actually still used. When you go from 1 to 6, that's a factor of 100. Of course, that didn't last forever, because by the 19th century, there was the advent of photography, and so there was a much more sophisticated system emerged. But basically, it kept the same idea from Ptolemy. But you had to introduce negative numbers for very bright objects. Okay, now here are some numbers. No need to write any of these down, but this just gives you a sense of how we compare apparent magnitudes. By far the brightest thing in the sky you're ever going to see is the sun, about negative 26.8. Notice that negative number. That's negatives are brighter than positives in this designation. Then after that you got a moon, full moon, negative 12.6. Venus, the next brightest thing, you've seen it already, negative 4.4. Sirius, the brightest star in the night sky, negative 1.5. By the way, there are no units for this. These are just designations for magnitude, but there's no actual units. Canopus is the second brightest star. The faintest stars you can probably see if you've got good eyes are at about plus 6. The faintest stars you can see from Earth are about plus 24. The faintest stars you can see with the Hubble are about plus 28. With the Webb, it's probably closer to plus 31 or plus 32. And of course, we're only still seeing some of the stars. There's plenty of stars that are not visible. Might even be the case that most of the stars aren't visible. Now, how do we think about this? I put this on a number line. Notice that my number line goes from negatives to positives. Negative, you got the far left, and that's going to be the brightest thing you got, which is the sun. Negative 4.4, Venus, negative 2.7, Jupiter, negative 1.5. We put 0 over here, and then 2, which is typically about what you see in kind of being close to a city. That's about the range. +6 is the faintest you're ever going to see with the naked eye, and that's only if you've got really, really, really dark skies. Negative numbers are brighter, positive numbers are dimmer. Magnitudes go from the negative, which is very bright, to positive numbers, which get dimmer and dimmer. And of course, the brightest nighttime objects other than the moon are going to be Jupiter, Venus, Sirius, Canopus, and some other, there's a handful of other brighter stars that I'll mention later on a table. Right here, in fact. So these are the 25 brightest stars in the night sky. You have not seen all of these. Not all of these are visible in the northern hemisphere, but you can definitely see Sirius. For sure, you can see Arcturus, you can see Vega, especially this summer. You can definitely see Rigel in Orion. Oh my gosh, what else can you see? Castor and Pollux are in the constellation of Gemini. You can definitely see Betelgeuse. Also notice the difference in color here. Now these aren't actual photographs of the stars, but they are designations. They kind of give you a rough idea of the color as well. You can see at least half of these. You can definitely see Antares and Spica. And also this summer you'll see Deneb. Now, nothing to write down here, but I want to briefly talk about the math of apparent magnitude because you can probably handle it. The magnitude factor is the fifth root of 100, which is really strange. That is 2.512. And that keeps the standard from Ptolemy, which goes from 1 to 6 as a factor of 100 times. That means when you go from one magnitude to the next, either brighter or dimmer, you go up or down a factor of 2.5. Now this is apparent magnitude, and that depends on the actual brightness or luminosity, the distance, and any stuff that happens to be in the way. As an example, let's say you got a magnitude of -1. It's 2.5 times brighter than a magnitude of 0. And since 0 is 2.5 times brighter than a magnitude of +1, -1 is 2.5 squared times brighter than +1, which is 6.25. That's what it works out to be. 2.5 squared is 6.25 brighter. So every magnitude represents a change of 2.5 times brighter or dimmer. Brighter if you are going from negative to more negative, and dimmer if you are going to positive to more positive. The brightness difference between -1 and 6. Oh boy, how many magnitudes does that happen to be? Well, that's 7 magnitudes. So that's 2.5 to the 7th power, or around 600 times apparently brighter. That is to say, -1 is about 600 times brighter than magnitude of 6. Let me briefly talk about absolute magnitude. That's how bright the thing actually is if you are a distance defined as 10 parsecs away. That's how we define it. It depends on the star's luminosity or brightness. It also depends on the radius and the temperature. That's the formula you certainly don't need to write down, but it is a classic formula in physics that relates the luminosity or brightness to 4 pi, certainly related to a sphere, r squared, the radius squared, times a constant of proportionality called the Stefan-Boltzmann constant, times the temperature to the 4th power. The fact that you see temperature to the 4th power should tell you that small changes in temperature make a big change in brightness. There's also a conversion between apparent magnitude and absolute magnitude, which is a logarithmic equation. This is here for your information. You don't need to write this down, but it's a nice relationship between apparent and absolute magnitude. Okay, now briefly, let's talk about a star's color. Star doesn't have one color. It actually has a combination of what could be thousands of colors, really, and a whole lot of non-visible electromagnetic waves like UV. The most prominent color is typically the peak visible light output, but there's a whole lot more to be seen. Usually we need a spectroscope or spectrograph or some special purpose telescope. Radio telescopes work really, really well to see the other electromagnetic radiation. Stars look very different in different ranges of the EM spectrum. Remember our EM spectrum. So we go from radio waves to gamma rays. You can see a whole lot more detail if you use devices that are especially made for that. In our next lesson, we're going to talk a little bit more about those details.